Welcome to lecture 12. So starting from the last lecture, we began to look at more closely at the environment. In particular, we would like to have a more explicit description of the environment. The need of this in designing a sort of intelligent agent system is that basically if we give up the assumption of complete information, it means that the agent will not be fully aware of the environment or the dynamics of the environment. In this case, there's a need to explicitly model the environment. Right? Today we're going to deviate a little bit from our discussion on multi-agent system, and instead we're going to look at arbitrary sort of agent-based systems. So this mainly we're concerning about single-agent systems. The reason is that we would like to build a sort of a more solid foundation on the modeling of the environment, and this will allow us to capture in a more realistic way the interaction between agents and the environment. So if you think about the interaction between agents and the environment, this is actually a fundamental theme in artificial intelligence, and in almost all the sub-areas of artificial intelligence somehow have some deep connection to this theme. So looking at the interaction, we can identify two directions. So the first one is going from the environment to the agent. The environment typically can be captured by a number of states. And these states are reflected through, for example, the combination of a certain environment variables or features. So the states in the environment actually determine the basic engagement rule between the agents. This involves what sort of action the agent may perform in that environment, what sort of rewards the agent may receive, the cost of performing these actions, or the cost of certain outcomes of the game. Right? Also, the environment produces signals for the agent to make observation about. So the agent is able to observe like what sort of states the environment is in and using these information to make inferences. So that's going from the direction from the environment to the agent. And then, of course, there's another direction that the agent in return could have the capability to make changes to the environment states through its actions. For example, if the agent performs certain operation like moving a block from a top of a position to another position, and then the environment will actually change. Right, then the loop will only be completed only after we describe the second direction. However, if you look at the models that we have seen so far, we've looked at, for example, the complete information game. They include repeated games and multi-stage games. We've also looked at incomplete games that are these Bayesian games. If you think about it, in the repeated game, a conceptual, so I would like to view it more conceptually like we are repeatedly playing some fixed stage game. So essentially you can think of that's the conceptual model of it. There's the same game, so sort of the environment stays fixed, and then the agents just interact within that environment. The environment doesn't really change. If you look at the multi-stage game, although the environment changes, but it changes in a very fixed way, so the agent will start from the first stage game and then move on to the second stage game and move on to the third stage game and so on. So the sequence of the stage games are completely fixed. It's not affected by the agent's behaviors. Right. And these are the complete information games. All the agents know exactly what's going on, so there haven't been any need to explicitly model the environment. We just need to embed all the information of the environment into the game setup. On the other hand, when we look at the Bayesian games, there's a need to model the environment. However, this is inherently a static game. There's no dynamics going on because the agent just make one simultaneous action and that's it, right? So although the environment may consist of several games, but really there's no interaction going on. The agent also does not need to change the environment, right? So we will need to have a more powerful model if we really want to, model multi-agent system who are functioning in the environment, who are dynamically interacting with the environment. And this is what we're going to do, but we move to what we call basically a simpler scenario where we only have a single player. And then in the next lecture, we're going to generalize it to multiplayer setup. Right, so right now in this lecture, we're only going to look at single-player games. In fact, this lecture can be suitably included in an earlier course in artificial intelligence, but I think that it's just to be complete. For this course, I will insert this lecture on single-agent scenario. Right, so we want to model the two-way interaction between the agent and its environment. Right, so consider the case, right? Ideally, we want to be able to, develop something like a computer game where we have a agent who's functioning within the environment, and then the game consists of a number of steps. Of course, some of the game may consist of lots of steps, but if you look at it, each step, the agent essentially performed several operations. So first of all, it's able to observe the environment. It's able to get information from its surrounding, and then the agent is able to perform actions. This could be moving ahead or jumping or shooting or doing some other things, and all of that will have an impact on the environment. For example, some brick just got broken, or some enemy got shoot, or some gold coins being collected, and so on. So the environment will be changed at some point, and then with each action, the agent gets a score. Right, the score can be implicit, it could be explicit, which is added to the agent, but it could be implicit, it could be just the progress of the game. That would be some sort of score. Then the gameplay consists of a sequence of actions, so the agent will perform a sequence of actions, and then the actions would result in certain outcome, and then from that state, there's another action that's being performed, and then the game going to a next state, and then repeat like that. So that's the overall procedure of the gameplay. And what does the agent want? The agent, of course, want to have a higher total score, right? So it's not just a score of the individual step, but it's the entire run of the game. So we're looking at the total score of that. The higher the score, the more successful the agent is. So this is a sort of a general setup that's applying to any of the situation that we want to look at that involve agent or a single agent interacting with the environment. And if we look at more formally, of course, this is a very simple special case, but this would be a good example. So it allows us to develop a unified language to specify models of the environment, or sometimes in AI we call it the world model. That's the sort of the representation of the environment that the agent is functioning in. And we would like to look at what the agent is able to perform and what are the consequences of these actions. So let's look at this very simple robot that is traversing within a space. Of course, the robot can be in lots of positions, but for example, we can build a very, very simple model which says, okay, the robot could be in any of the two states. Either it has high power or it has low power, because the robot is battery powered. The battery can have high power and it could have low power. And the robot has two actions that it can choose to function within the space. It can either wait, or it can start to search, and by searching, it could be searching for some item, or it can be searching for some dirt. There's a third alternative, which is to go and recharge, because if it continues to function in the space, it would just eventually die off power. So if the robot continues to search with certain probability, it will power off and needs costly manual restart, and this is not what we want. So we need to explicitly build in this cost of restarting, of manual restarting, into our model. So one of the models that we can build, which is very simple, consists of this picture. Basically, it has two states, high and low. And notice that the agent, which is a robot, will be able to either wait at a particular state or began to search at a particular state. But we know that, also at low, it's slightly different, because at low, the agent is able to search or wait, but is also having the option of recharge. Right? The recharge is an action is only available at low state. Right? So if it's high state, there's no need to recharge for power. And also, with each of these actions, you can see two other variables. So one of the variable that is a value that's between 0 and 1. So this indicates a probability. And it's a probability of state transition. So this basically means that if the agent is at low state, that the energy is low, then and if the agent chooses to recharge itself, then with probability 1, so with 100% probability, in the next period after recharge, the agent will go back to high state, right? It'll go to high state. For example, if another example is when the agent is at high state, and suppose it chooses to wait, right? Wait doesn't really consume a lot of energy, so with probability 1, the agent will stay at high state. Right. But if the agent chooses to perform a search, right, it's still able to stay at high, but only with probability 0.5, right, with 50% probability. But what about the other 50%? We can see another arrow that going out from high state to low. So with 50% probability, the agent will move from high state to a low state if it chooses to perform a search at this state. So, and you can see that with every state and with every action, the agent will have a number of arrows pointing to either the same state or other state, but then the probability that's on top of these arrows must add up to 1, right? Because it's capturing, all of the cases. And there's a second value that come along with each arrow here, and that indicates the one-step reward, so sort of like a local reward of the agent. For example, if the agent start to recharge and moving from low state to high state, the reward is actually 0 because it didn't really perform any work. Right. We could, for example, associate another variable R wait. That's the reward of waiting. So if the agent is at high and it chooses to wait, with 1 probability, it's going back to a high state, but the reward would be R wait. Right. Similarly, if it chooses to do search, the reward will be R search. Right. So you can see that from high with 0.5 probability, we get a reward of our search and go back to a high. With another 0.5 probability, it will move to low state, but the reward will be just search. Right. So we have this description of the system. It's essentially a finite state model. That we call it a Markov decision process, and that's a very basic model which allows us to describe the environment and also how the agent is functioning within the environment. So basically the dynamics of the environment. This includes state transitions and rewards. Right. So more formally, a Markov decision process, or MDP, is a 4-tuple, well, it's actually a 5-tuple here. I modified the definition a bit, where we have S, A, P, R, and then we have the fifth element, which is gamma. Well, actually, in most textbooks, you just find these 4 elements, but then gamma is a discount factor, because in this course, we were only looking at discounted total payoff. But I'll describe it in the next, in another slide. But here we have a set of states in the environment, right? If you imagine here in this example, we have 2 states. So we have a set of states, and we call it S, and then we have a set of actions that are available by to the agents. Right. And then we have these transition function, but it's a probabilistic transition function. So when the agent at a particular state and performing a particular action, there's a possibility of transiting to other states as prime, and the probability is indicated by P of SAS prime. And for convenience, we just write it in this way. So capital P with a superscript A with a subscript S arrow S prime. That indicates a single probability between 0 and 1 for this transition to take place. That's the probabilistic transition function. There's also the possible, the agent may also get a reward out of this transition. So given the transition SAS prime, we associate this R. So R of that will be the immediate or sort of like a one-step reward for the agent from, basically performing these transition, right? And we denote this RSAS as prime also conveniently by R with the superscript A and the subscript S arrow S prime, right? So essentially, the dynamics of the environment can be described by these four components, and then there's a gamma, which is a value between 0 and 1, which is the discount factor. So in this course, I assume that when we present the Markov decision process, the gamma is already fixed, but in fact, that this gamma can be modified in real application. But let's see. So how do we play, and how do we run this MDP, right? So in the literature, people typically call it a run, but because we are dealing with in sort of a game theoretical scenario, and we can view this MDP as a model of a single player game, right? Remember, and therefore we also call it a play, right? So it's a finite or infinite sequence of decisions made by the agent and states that correspond to these decisions. So more formally, we have the sequence S0, which is the initial state, and then the agent performs A1, which is the first ever action that are available at this state, and then the agent will get a reward R1 out of this action, and then the system will make a transition to the next state S1. The agent will perform A2, getting a reward R2, where the system will make a transition to S2, and so on and so forth. So you can see that these blue S values, that indicates the sequence of states that the environment is in, and then the green sequence of A1, A2, A3, that indicate a sequence of actions performed by the player at the corresponding states, and then the orange values R1, R2, R3 are the immediate rewards that are received by the agent out of each of the respective transitions, right? So that formally describes how the MDP may run, but that's only a sample run. So it's only one instance of a possible run of the whole system. If you look at this example where we had this robot who are in these two states, H and L, so high and low, and then the action space consists of search, wait, and recharge. Then we could, for example, define a play in. That's the table of probabilistic transitions and rewards of the whole MDP, right? So we have the starting state. We have the possible actions performed by the agent. You can see that at high, we're going to be able to perform search and wait. At low, we're able to perform search, wait, and recharge. Of course, we can have an assumption that says that the set of actions of the player available at all the states are the same. Right, so in this case, we can have high where the agent perform recharge, but we can just make them trivial. So the state would be staying in the same place, and there's no reward, and probability 1 and so on. So we choose to ignore those trivial transitions. And here in this column, we indicate all of the probability for the transitions of happening. And the last column indicates the immediate rewards that could be received by the agents. So we have these full description of the MDP now, and one of the possible plays, there can be a lot of plays. There can be actually infinite plays if we are allowing infinite sequence of plays. So one of the potential play would be, the agent stay on high and then wait and then get a reward for the waiting, and then it stay at high. You remember that it's one. With probability 1, it will stay at high, and then the agent perform a search and get a reward out of the search, and then with 50% chance it can move to low. So suppose in this play it indeed moves to low, and then it decides to recharge, of course getting 0 reward according to the table, and it becomes high, and of course this can be extended. I'll notice that I did not mention that we have a negative reward. So -3 here, this is when the agent is staying at low, yet it chooses to do search. And you can see that the next state is high. So without recharge, you go from low to high. How can this happen? Well, this can only happen when you have a manual restart of the agent, right? And remember, the manual restart consumes some resource, and it's costly. And so this -3, that's the cost of this manual restart. So intuitively, we can view a MDP as a single-player infinite stage game. So that's because with every action that the agent makes, you can think of it as a stage, right? So in one of the stage, the agent will be in one of the state, and that state you can think of it as a one static game. And then when the agent makes an action, there's a state transition from one state to another state, and then the other state, the agent actually plays that stage game. So you can think of it as a infinite sequence of possible stage games that are specified by the MDP. So each state of the MDP will be a static game, and they are connected together by these probabilistic transition function, right? So inherently, that's the sort of connection between the model that I present here and what we have talked about. The only difference right now is we're only looking at a single player case. Of course, like what I said in the next lecture, we're going to look at multiple player case. But the layout will be, you can see that very consistent with what we presented earlier. Right? For example, in this slide, we can imagine a Bayesian game. Even though it's a static game, it basically is just an MDP where we have a number of starting state, and each of the starting state has a certain probability of having the play started at that state. And then in the Bayesian game, we'll only care about one action, right? So we're not actually looking at the sequence of actions. If you recall repeated games. In a repeated games, we just have one state of the game, and there's a deterministic transition that go from that state back to itself. And the agent just repeatedly playing in that same stage games. Right? And if you record the multi-stage game, there will be a number of states that are connected in this linear way, and you can only go from one state to the next state, and from the next state to the third state, and so on. So the order of the states transition is fixed. So the repeated game and the multi-stage game that we introduced earlier allows only deterministic transitions, only fixed transitions, regardless of the agent's actions. So this is indeed a much more powerful model. This Markov decision process is indeed a powerful model because it allows the agents using its action to influence the states of the environment. So in fact, the state of the environment depends very much on what actions are chosen by the player. Right? So that's the crucial thing. Right? So you can think of the sequence of stage game to be played is not fixed, but rather it's determined by the actions of the player in a probabilistic way. Of course, there's a certain randomness or uncertainty within the environment. The transition probabilities represent somehow the beliefs of the player about the environment. Right? Given the player is in the state S, assuming that the player performs an action, the transition probability represents the chance of moving into a specific state in the next stage, right? So that's also in line with Bayesian games where we have this prior probability. So you can think of that as a sort of like an initial transition that going into one of the possible stage games. So that's how I want to draw a parallel between MDP and the model that we introduced earlier. And also we can draw this game tree. Of course, this is a single player game tree where each node is belonging to the same player. So you can think of it as just a decision tree by the agent. But also with each of the edges in the tree is probabilistic, so it has to be labeled by the corresponding probability. And because we are mostly concerning with MDB with infinite run, so the game tree will be an infinite height tree. So in principle, the agent's behavior depends on the entire history of play. So what I mean by that is whenever at certain stage, remember if we view the whole thing as a stage, multi-stage game, right? So imagine at a stage T, the agent is trying to make a decision on what to do. In principle, the decision should be made based on everything that has happened from stage 1 up to stage T, right? And the agent will look at the entire run of the history and said, okay, now I'm going to do this. However, this is why we call it a Markov decision process. Markov is we can imagine that very importantly there's a Markov property with this description of the system, namely the future state or let's say the next state of the system depend only on the current state, but not on the earlier state. This makes the description of the system much more compact and much easier to analyze. And therefore, we would like to keep ourselves within the realm of Markov processes. And because of that, we usually assume that the agent's behaviors are also satisfying the Markov property. Right? And this means that the agent, when it tries to make a decision, it will not really care about at which stage it is making the decision. It will not care about what has happened from stage 0 up to now. It will only concern about where the current state is. And based on that, it makes a decision. Right? So this is what we call a strategy in an MDP. Right? So this is essentially a Markov strategy. Right? And also mostly in the study of MDP and in like reinforcement learning and so on, that's also called a policy. But just to be consistent with the game theoretical analysis that we've done so far, I call it a strategy. So a strategy of an MDP is a function pi which maps states to actions. Right, so essentially it's a rule book that's presented to an player, and it says, okay, if you're in this state, you're going to do this. If you're in some other state, then you do that, right? So the only factor that determines the action of the player is which state it is in, right? So that's essentially a pure strategy in this way. So of course you can generalize it to study what we call behavioral strategies. We call that, and a behavioral strategy is saying that if you're in a certain state of the game, then with certain probability you're able to perform this action, and some other probability you're able to perform that action. So you actually have you can allow certain mixture of actions, but of course we can define the same sort of type of policy for MDP. But just to make my lecture sound easier and without having too much tedious symbols, I will fix on just pure strategies. But bear in mind the possibility of having these behavioral strategies also. So if we have a policy, right, it essentially determines a probabilistic distribution of runs. So what do I mean by that? So if you look at all of the possible runs in this MDP, and each run, so given this strategy, each run will occur with certain probability. And what's the probability? Suppose you have a run, right? And this, I'm only talking about a finite run here. So this run will have, S0, pi S0. This pi will be the action that's taken by the player at S0, and then getting a reward, and then all the way down. And this will be one history of the gameplay. The occurrence of that history will have a probability which is equal to the multiplication of all of the transitions that taken place in that history, right? So that pi is the multiplication of all of these probabilities. You can look it up from the probability table and you multiply them. That will be the probability of this history. After we define the behavior of the player, the next thing that we need to define in this model is basically the outcome, and the outcome determines the payoff to the player. And because we are more interested in the infinite run case, where the MDP is assumed to be able to run in, for infinitely many stages, we would not so much care about the actual outcome. The outcome will be just the infinite play, and then we want to define how much payoff that the player will receive. And like what I said when I presented the definition of Markov decision process, we said that we are interested in discounted payoff. And remember, as part of the definition, we fix this discount factor gamma between 0 and 1. And remember, it's strictly less than 1. So essentially, we're dealing with exactly the same situation as in the repeated game. Remember, in the repeated game, we also are interested in these discounted payoffs, where suppose you have any sequence of plays, the payoff will be equal to the payoff of the first stage plus the gamma time to pay off the second stage, plus gamma square time to pay off the third stage, and so on. Right? So we call it the expected value function, or just the value function, and I use the capital V to denote this expected payoff. Pi is a strategy of the player, and so I write V superscript pi S, as this S is a state. So this is the expected reward for any play that starts from the state S, assuming that the player will follow the strategy pi. Okay, so suppose that would be any play that are generated that are consistent with the strategy pi. Remember, this means that this play will occur with the certain probability which is defined in the previous slide. The expectation on the gamma discounted payoff, and this gamma discounted payoff, you can think of it as essentially a ex ante payoff, because we are looking at this payoff without actually playing the game. We're just at the state S, right? So you can think of it as an ex ante payoff, because the play hasn't really happened yet, but we want to calculate the expectation of that. So we have the discount for every later stages. Bear in mind that if you read another book on Markov decision process or reinforcement learning and so on, people typically introduce two types of payoff functions. So gamma discounted payoff is one of the most widely used one, but there's another type of payoff function, namely average payoff, and this typically refers to finite run. So after a finite run, the agent will get a payoff which is not the discounted one, but it's sort of like the averaged payoff among all of the stages. That will make potentially analysis of the game more complex, and certain results that I will present in the lecture will not hold for the average case. But just to be simple, we're presenting the gamma discounted payoff. As what I said, this is a very, very well-known and well-studied and widely adopted payoff function. So we are interested in solving a number of problems on Markov decision process. The first problem that we want to tackle is to really compute this expected payoff of the player, because it's not trivial at all how we can evaluate how much payoff expected to be received by the player. Right, so that's a very, very important and fundamental problem. We call this the policy evaluation problem. In some books, it's also called the prediction problem of MDP. Also, because we're dealing with strategy, so I also call it a strategy evaluation in the future. So essentially what the problem says is we suppose we're given as input an MDP, and suppose we have a policy pi. And now what we want to do is we want to evaluate the expected payoff of the player if it starts from any state in the MDP. So we want to obtain the value function v pi. So to calculate the value function v given the strategy pi, we can refer directly to the definition of the function. So by definition, it's the expectation of the discounted rewards. But starting from any state S, that expectation, if you look at all of the possible outcomes after one action, we're essentially looking at all of the possible transitions that the player can make out of S. So essentially, we just need to look at all of the possible next states S prime, and then we'll look at the probability of the transition from S to S prime following the action as specified by pi. Right. So given the action pi S, remember that's the action that the player will play according to the rulebook pi. And starting from the state S, the probability of going into S prime is given by this probability. Right. It's given by this probability. And then we need to multiply by the expected rewards that the player will get. And this consists of two parts. The first part will be the immediate reward out of this particular transition. So that transition from S to S prime will give certain reward to the player. So this is captured by this R. And then there's a second part, which is the same valuation function, the same value function v of pi, but starting at the state S prime. Right. And of course, because this is the expected payoff, but only after one transition. So all of these sum, so this discounted payoff should be further discounted by gamma. Right, because that's the action that's taken after the first action, right? So altogether, we have this sum, which is the immediate payoff, the immediate reward, plus a discounted value of the expected payoff, future payoff, starting from the next state. And we sum all of this for all of the possible next state, right? So that, by definition, should be the same as v pi of S. So notice that we are here using a technique which is called bootstrapping. So bootstrapping is a technique that when we want to evaluate a function, we're essentially using the function itself, sort of like in a recurrence way. Right. So without knowing anything about the function, we can draw this relationship. This is the recurrence relationship from to derive v pi of S. We can use the evaluation at other states S prime, and then we can apply this formula. So and calculate the sum to get v pi of S. Right. To make this formula look easier to read, we let Ra of S for any action A to be the sum over all of the S prime in S the product of PAS goes to S prime times RAS go to S prime. So you can see that this is what we get by expanding the product out of all of the S prime here. So this term, that's equal to RAS. And then we can rewrite the equation above. And this way we have the V pi of S is equal to RS of pi S. Remember, pi S is an action, so it takes the place of A here. And that is the sort of the first part. And then in the second part, we'll have the discounted part. We'll have the discounted payoff, so we have the gamma multiplied by V pi of S prime. But this should be summed over all of the S prime and then multiply with the corresponding transition probability going from S to S prime, right? So we have this equation. Again, this is the recurrence equation that calculates V pi of S from V pi of S prime for all of the S prime in S. And this is called the Bellman equation, or in particular, this one is the Bellman expectation equation. And this will allow us to compute the expected payoff of the player starting from starting state S. Right. And the technique of what I've described, basically this bootstrapping idea of using this recurrence relation to and iteratively to approximate the true value. So basically computing the strategy evaluation problem is called dynamic programming. So that's the dynamic programming idea that has been used in a lot of the scenario that we have looked at. For example, when you were studying in second year algorithm courses, you may have heard about the Floyd-Warshall algorithm for computing all pair shortest paths in a graph. That's a dynamic programming algorithm, right? There are lots of dynamic programming algorithms that I assume you have seen, but in particular, the idea is always this: we identify some sort of recurrence relation, and that's in the form of a Bellman equation. And then what we can do is we start with some initial valuation function, and this valuation doesn't have to be fixed. It could be some arbitrary valuation function, and then iteratively we update the value, so hopefully in the limit, so that means as k goes to infinity, it will converge to the right evaluation, right? This technique is what I call bootstrapping, estimating the value of states based on the estimation of the value of states, right? So in practice, what we do is we let Vk of pi S, we have these extra parameter k, to denote the expected discounted accumulative reward for any run of length k starting from S. Right? So remember, we're interested in actually infinite k, right? So what we do is we, starting from V0 pi of S, this is some initial value, and then we iteratively apply the Bellman expectation equation, right? In this way, just apply the equation that we derived earlier, and then iteratively, starting from Vk, we arrive at the next function Vk plus 1, and then Vk plus 2, and so on. Eventually, when it converges, we say that's the value function that we were looking for. That's the algorithm, the pseudocode of the algorithm. The input would be MDP and a policy, and the output would be the expected reward function. And essentially, this is what we have discussed earlier. How do we check for convergence? This doesn't have to be exactly, when V absolutely converges. It could be just when the next V is within certain distance from the current V, then we can stop the repetition in actual applications. So if you look at this example, this is a typical example of a grid world where we have a number of states that are in the grid. The states, altogether there are 16 states from 0 to 15. And the action of the agents could be going up, down, left, right, as in any grid world situation. The state transition are all deterministic, so just, because we want to give you this example, so just imagine this is all deterministic transitions, and with every action, there's a reward. The reward will be -1 because it consumes energy to move one step. And now we fix a strategy, which is the absolute random strategy. This would be like a random walk policy. This will be, starting from any state, we can go up, down, left, right, but all with probability 1/4, right? You can see that this is not, strictly speaking, the policy that I defined, because when I define the policy, it will be a deterministic, so it will be a pure strategy, right? So starting from any state, we make a move, a fixed move. But here, this is more like a behavioral strategy. But I've said that the definition, when I define policy, can be extended to a behavioral case, right? So that would be just exactly a behavioral strategy. So now you can see the state transitions are actually deterministic, because this assumes that all of the transition has a probability of 1, but the strategy is random. And now we want to evaluate this strategy in this context. And what are we going to do, right? The gray positions, that's 0 and 15. These two are target positions, right? So the reward is -1 for any action until a target is reached. And when we reach a target, we stop, right? This is assumed that we stop, but you can also imagine that when we reach a target, we're just stuck in the target. So this is the absorbing state, and it has 0 payoff, right? So now let's look at, when k is equal to 0, let's suppose that the all of the initial value will be 0, right? This is when nobody has to make any move, and the valuation could be initialized to 0. And then after one iteration, we're looking at the value that the player will get if it is after it has made one move, right? After it has made one move, and that would be -1. So basically, we derive this table from the previous table, and then we apply Bellman equation, right? We apply Bellman equation. We also apply a discount factor of 0.4, right? So with this, starting from this node, it can either go up, left, right, down. But when it goes up, it cannot move, so it just stay at the same location. But still, there's a quarter chance of going up, right? And because the initial table have all 0 values, so all of these values will essentially be the same after one round, which is -1, right? Remember that -1 is a transition that it takes to make one transition, unless the player is in the target state. And then we go on to the next state. So suppose the player make 2 actions, right? And what will be the corresponding value for each of the states? So this will be the expected payoff of the player if it starts from this state and make 2 transitions. Right, make 2 transitions. This can be derived using the Bellman equation from this table, right? And if you do the calculation, you'll be able to see that this indeed give you -1.3. The -1 comes from the fact that you will make one move, and every move will take -1. But because we have a gamma of 0.4 here, if we go either up, right, or down, so let's suppose we're starting from this location, right? Starting from this location. If we go up, right, down, the payoff that we will get will be a quarter of -1, a quarter of -1, and a quarter of -1, right? So that will give us essentially 3/4. 3/4, right? And then we multiply by the discount, which is 0.4, right? So 3/4 times 0.4, that'll be essentially 0.3. Right? Of course, this is negative because all of the payoff are negative, so we got negative 0.3, and then plus the negative 1, which is the cost of performing one transition at this current state. This will give us negative 1.3 as a reward, as a payoff for this location. Right? And this location have negative 1.4 because there are, in all of the 4 directions, we're going to create a negative 1 payoff. Right? So after 2 steps, we're going to arrive at this table, and then we perform the same action, or the same calculation to move on to the next step, which is k equal to 3. We'll get this table. Essentially, what we're aiming for is the control, so optimal control of the agent. Right? Formally, the problem will basically ask for a policy or a strategy that maximizes the rewards of the agent. Right. So formally speaking, we've got a input MDP with a certain initial state. We've got what we wanted was the optimal policy that, starting from any state, moving to an action. Notice that here we're actually looking for a pure policy, not just a behavioral policy, right? We're just looking for the pure policy that directs the agent to move from every state. But we would like to make sure that so essentially the policy that we're making will allow us to get the maximum value from any given state. So pi star essentially will be the arg max. So that would be the pi that enable us to get the maximum value. Right? And how are we going to solve this problem? We're going to use 2 algorithms, which we call policy iteration and value iteration. You see that if we have solved this problem, then given any MDP, we'll be able to design an agent that functions within the environment in an optimal way. Right, so this is really, really good. And let's see how we're going to solve it. We're going to look at this function. Instead of focusing directly on the valuation function, we also introduce a second function. Essentially, it plays a very similar role as the evaluation function. The only difference is that here we're making an evaluation not just from states, but also from state, but given a particular action that the agent may take. Right, so this is called the action value function, and I call it the Q. This letter will be very influential, and it will appear numerous times in the next lectures. So we call it a Q with the superscript pi because we're still following very consistently the strategy pi, and then it's a function that's given S and given a action A. It returns a value, and it returns a payoff value, not just the immediate payoff, but an expected payoff for all the future plays, assuming that the player performs action A at state S, and then after this transition, the player just follows the strategy pi, right? So that's the meaning of the Q function, right? So Q of SA given pi will be the expectation of, again, this is very similar to the valuation, so it's just basically discounted sum of the corresponding payoff, but the only difference is that this S0 is is S, and A0 is A. But then all of the rest of the plays are consistent with pi. Right. So by definition of V pi, we'll get a direct relationship between Q pi and V pi. So Q pi, given S and A, will be the immediate reward R of SA, right? Remember, that's the expected rewards because this is the sum of the reward of all of the possible transitions from S to S prime. And then we take the discount gamma, multiply with the value at any next state S prime, and then multiply with the probability of moving to that state, and we take the sum, right? So that's the expectation of the payoff that we will get after the first move. And the sum is our action value prediction, right? So Q of SA. So this basically means that V pi of S, remember V pi of S will be the evaluation that we get if the agent follow pi O along, right? So that would be just Q of pi starting from S, assuming that the agent would just perform exactly the action directed by pi, right? So S of pi S. That's the relationship between the V function and the Q function. So essentially, they're very similar, but working with the Q function is preferable especially when we solve the optimal control problem, because this gives us a freedom to choose the actions, to look at the consequence of performing an action at a given state. So let pi star be the optimal policy. So that's the policy that we are aiming to find. Right. And then we can define this value of V star as, so defined as essentially V pi star of S. So this is just rewriting the V pi star of S as V star of S. So that's the optimal value that we will ever get out of any policy, because that's the payoff that we get out of the optimal policy, right? And that will essentially be according to the relationship between V and Q. You can see that this will be essentially we look at all of the Q values which are consistent with the optimal policy. Right? We look at all of the Q values starting from S and for any possible action of the player, but we choose the action that gives us the best Q value. Right? And that value that we get, that payoff, that expected payoff that we get out of these, all of the possible actions and take the maximum Q value, that will be equal to V star, right? That will be equal to the optimal value for the state S, right? So in this way, we actually can derive a corresponding Bellman equation, but write everything in terms of Q, right? Because we know that this V value can be derived from the Q value, and also because of the correspondence between the Q value and the V value, right? So because of that, we can rewrite the Q value at the optimal policy as first of all, we have the immediate payoff. So that would be exactly, we do this, but replace this part by the corresponding Q, right? So we have this RAS and then times gamma times the sum of the probability multiply with the V value, but the V value is equal to the maximum of the Q value. So this is just the probability multiply with the maximum of the Q value. How do we actually use this to solve the optimal control policy? We use this technique called the policy iteration. So we aim to find the optimal policy, but we don't know the optimal policy, so we start with some random policy, right? We start with some random policy, and then what we do is we evaluate that policy to get some value V, and then we can improve the policy by acting greedily with respect to Q pi, right? So what do I mean by that is, once we get this valuation, we know that, well, from a state, what action will give us how much payoff, and then we just need to choose the action that gives us the maximum payoff for that state. And then if we do this for every state, we'll potentially be able to improve the performance. We'll be able to improve ourselves to get a higher expected payoff, right? You can see that this is almost like learning for the agent. It starts off with some arbitrary policy, and it's not optimal at all, but it sort of evaluate this policy and see that, okay, with this policy, and if I perform action at every state, I will get this value, and then why do I keep doing this keep following this policy? I would instead switch to other actions that may give me a higher payoff. So the agent would just switch to the other policy, but then this makes a new policy. So this is an improvement step. So when we reach the improvement step, we're going to get a new policy, and this requires another round of evaluation. And after another round of evaluation, potentially the valuation function may be different from the original value, from the earlier valuation function. And this means that looking from the perspective of the agent would say, well, maybe this other action will give me a higher payoff. So it switches its policy and improves the policy. Right, and once it improves the policy, we got a new policy, and this, calls for another round of evaluation. So essentially, we're going back and forth. We starting with policy, evaluate it, and improve it, and then evaluate it, improve it, evaluate it, improve it. But what we can guarantee is that at each step, the agent is actually making a greedy choice to improve its current policy. And we can guarantee that this improvement will actually make the policy better. So the expected payoff for the player will get higher and higher. All right, so eventually it will stabilize because there are only finitely many policies out there, right? So eventually it will stabilize and converge to the optimal policy that we are aiming to find. All right, so if we repeat this iteration, eventually we're going to arrive at this policy. So this policy, when we arrive at this policy, means that starting from this policy, we evaluate it to get this value, and then if the agents try to change their action, but they did not actually change their action because the current policy is already the optimal one. So after this improvement, we can see no improvement at all. And this is when the procedure stabilizes and converges to this optimal pi. All right, so this is what we mean by policy iteration. It consists of two parts. We have already specified how we perform the evaluation step. So I'm going to skip that, but we will still need to talk about how we actually perform the policy improvement. You can see this is really simple. What you do is, suppose you have evaluated your V function, then you just need to modify your strategy correspondingly, and the modification of the strategy is sort of like the optimal. So you just choose so suppose you have V function, you can then calculate your Q function from the V function, and once you have that, you just need to, for every state, select the action which give you the maximum Q value, and then the new action will be assigned to the updated strategy pi. So this pi prime is the updated strategy pi. So this will be one iteration of the policy improvement. Right, and notice that we can, in fact, prove mathematically that the value that the player will get starting from any state will be no less. So for the updated strategy, will be no less than the value from the original policy pi, and because of that, we would eventually see a convergence of the policy if we repeat the process. Right? So if you look at this example, the same example of a grid world, we have these many states starting from all zero values. We're starting from the random policy. We're starting from the random policy, and that's the random policy. Right? And suppose the agent makes one move, it goes into this policy, and if you correspondingly adjust the policy, so this will be the strategy improvement after only one step evaluation, you can already see that the action of the player changes, right? Because starting from this location, if it goes either right or down or starting at itself, it will get -1 payoff. But if it moves to the left, it will actually get negative payoff. It will actually get 0 payoff. So 0 is better than -1. So from this location, the player would tend to this left-hand side location. Right. On the other hand, for any of these locations, the player still is undecided, so still just playing the random strategy. But if you go on to the next iteration, so suppose the evaluation is performed here, and then suppose we improve the strategies from here to here, then you can see that starting from this location, moving left will give the player -1.3, but moving right and down will give the player -1.4, and also up will also give -1.4. So the player will instead choose just to go left. Right. So after only 3 steps, you will be able to see that now the players are adopting the optimal strategy. Right. So you can see that this is almost like learning. I would not call it learning, although in a lot of the literature, or most other cases, people call it model-based learning. So this is essentially, we're presenting a full picture of the environment and its dynamics, and the agent essentially, through the improvement of the policies, it iteratively identify the optimal policy. I wouldn't call it learning because all of these procedures can be performed offline, right? So it's just you take the policy and then you just run the algorithm. It would just produce you the optimal strategy. It doesn't really try the different. It doesn't need to try the different strategy. Everything can be computed offline. So that's the overall algorithm. What we do is we repeat between the policy evaluation and policy improvement, starting from any state. And initialize the value to 0, and then we have some random initialized strategy for the player. We repeat the loop, and in each step what we do is we perform 1 round of policy evaluation, and then we perform 1 round of policy improvement, and then we repeat this until the policy converges, and that will be the actual policy, the optimal policy that we were looking for. So the output pi will satisfy the Bellman optimal action equation, because you can see that this is guaranteed because eventually pi converges. Right. So that's policy iteration. Let's look at another application of this algorithm for the grid world example. Optimal policy is reached after 1 round of policy evaluation plus policy improvement. But this may not be true in general because the previous example is just so simple. If you look at this example, we have a car rental company who would like to use an automatic scheduling agent. And suppose that the car rental company runs in 2 locations, the city and the airport. And in each location, there are a number of cars that can be stored. But the space is limited. So at each location, we can contain a maximum of 20 cars. Right. So altogether, there are 40 states. It depends on the number of cars in each of the locations. Altogether 400 states. Right. 20 by 20 is 400. And we can perform certain actions, and the action could be we can, for each day, each night, we can transfer a number of cars, not cards, that's a typo, number of cars between the locations. So I can say move a number of cars from the city to the airport. So also, there's some external sort of input which rents the car out, right? So for every car that's got rented, either from the city or from the airport, we'll get a reward of $10. But the requirement is that you can only rent a car if it's available at that position, right? So what are the transitions? There are possible transitions that the cars were returned and requested randomly, right? So there's indeed an element of uncertainty with the environment. And we also can typically model such a event if we know a bit of statistics. Poisson distribution is one of the classical distribution that are able to model these rare events, such as car being returned and being requested. So we can actually model it using a Poisson distribution with a parameter lambda, So we also get, for the airport and the city, the different parameters. For example, in the airport, the average request is equal to 3, so this lambda would be equal to 3. So this lambda calculates the average value of occurrences of this event. So in the case of request, that would be the average number of requests, and in the returns, this lambda would be the number of average number of returns. So at the airport, this lambda will be 3 and 3. At the city, this lambda will be 4 and 2. Okay. So that's the setup that we have. We have these MDP, and we set a discount of gamma equals to 0.9. Assume this is given to us, and then we would like to find the optimal control, and we do this by initializing the sort of like the random actions, and then iteratively we improve the action. But once we improve the action, we need to reevaluate the strategies. So starting from O0, and what do these grids stand for? So essentially, every grid, I did not really draw it, but in fact, there are 20 possible values for the horizontal axis, and there are 20 values for the vertical axis. So you can imagine this is a 20 by 20 grid, right? And each position of the grid, there's a value, and this value will represent the action that we should take. And initially, I assumed that I perform these trivial policy where, regardless of the state I am in, I will move 0 cars between the two locations. And then I evaluate this strategy. And then once I evaluate the strategy, I perform this greedy update that give me this new updated strategy. At this new updated strategy, you can see that here at these states, I should be able to move, according to the strategy, I should move 5 cars from location 1, or from location 2 to location 1. So vertically, this represents the number of cars at the first location, right? This quadrant here represent the cases when we have quite a lot of cars at the first location and not many cars at the second location. So this 5 means we're transferring from the first location to the second location. And here we have essentially not many cars at the first location, but we have some cars at the second location. So here we do not do anything, but here we're actually transferring back. So we're transferring from the second location to the first location. This is represented by these negative numbers. And then iteratively, you can see that we improve the strategy, and then we reevaluate, improve the strategy, reevaluate, and iteratively converges. It converges to something like this. Right. This will be the optimal control that's found by the policy iteration algorithm. So now that finishes the description of the policy iteration algorithm. As I promised, there are 2 algorithms that I will present. The other one is value iteration. And the value iteration, you can think of it as another version of policy iteration, but it's a more direct way of finding the optimal strategy. The reason for we changing the policy iteration algorithm is that the disadvantage is that in the policy evaluation, the convergence to the corresponding value function occurs at the limit. So this may be quite slow, because in the policy iteration, we assume that we adopt a certain policy and then we evaluate it. But the evaluation itself is a dynamic programming process. So we need to repeat for a number of iterations until it stabilizes, and then we greatly improve the policy. That's quite efficient, but then we still need to evaluate, and the evaluation is always quite time consuming. So we would like to be able to converge to the optimal policy, but without the need to evaluate every intermediate strategy. In order to do that, we look at a principle which is called the principle of optimality, and essentially we have derived this in an earlier slide. So if we are interested in the optimal policy pi, and suppose we already computed the optimal the valuation function that corresponds to the optimal policy, namely the function v star, basically we can get a characterization of the optimal policy, so that for any state S, the action that should be taken at the state S, namely pi S, should be that action which gives the highest expected payoff. Right? So this will be the action A, which maximizes for every possible next state S prime the possible valuation that we can get by performing A to that state, and we add the all of the possible payoff up, right? So basically, if you look at the equation, it says that this is the action A such that it maximizes the sum for all of the S prime and S of the product between the probability of PAS transferring to S prime multiplied with the RAS transferring to S prime plus the discounted reward of the optimal valuation function, so gamma times V star of S prime, right? So this is essentially saying that this, in order to find the optimal policy, what we need is basically to compute V star. So instead of repeating this loop between the policy evaluation and policy improvement, we can avoid this repetition by simply aiming to compute V star. Right? So how are we going to do that? Well, this requires analysis of the function V star. So V star at a particular state S, we know that this is the optimal value function, right? This is the optimal value function. This means that this will be equal to, if you look at all of the actions that are available at state S, we pick that action which gives us the highest value action payoff, so which gives us the highest Q value, right? So among all of the A and A, we look at Q pi of SA that gives us the highest value of that, and that V star of S will be that maximum value of Q. But then we can expand this function Q pi star to, by definition of Q pi star, we can apply these Bellman equation for Q to say that this is equal to, look at the max among A and A of the value of RAS plus the discount. So basically the gamma multiply this sum the products of the probability multiplying the maximum of the Q function among all of the A prime in A, right? So that's the second line of this equation, and of course we can expand it further to rewrite R of AS into its original form, which is the sum of all of the next state S prime of the P times P of the probability AS transferring to S prime multiplied with S transferring to S prime. And then we do some algebraic manipulation, and eventually we'll arrive at this expression which says that the V star of S is just equal to the maximum value that we can get out of all of the actions available at S. The maximum value of the sum of all of the product of the form, basically the probability of the transition from S to S prime given action A, multiply with the payoff that we receive out of that transition plus the discounted values or the discounted payoff of the next state, which is the gamma times V star of S prime. Right? So that will give us another Bellman equation, and we call this the Bellman optimal value equation. And because of this allows us to again use the idea of bootstrapping and dynamic programming to evaluate the function V star. And notice that we can do this without going through consideration of any of the strategies. Here, when we are evaluating the V function, there's no superscript pi, right? So this V star is assumed to be the optimal one, and we are actually not actively evaluating any strategy. We're essentially just improving the value of the strategy. So the strategy is not explicitly present in the algorithm. It's rather implicitly obtained through this iteration, and explicitly we're just computing the corresponding value function V, right? So that's the overall procedure of this dynamic programming algorithm for value iteration. We will define Vk of S as the optimal payoff for any run of length k starting from the state S. And then we repeat a number of iterations, and in each of the iteration, we just recall the Bellman optimal value function. So starting from Vk, applying this recurrence, we'll be able to compute the next values of Vk plus 1 of S. Right, and if we do this iteratively, going from V1, V2, V3, and all the way until eventually the valuation function stabilizes. So convergence, the final output will be the limit. Right, so this is almost the same as the strategy evaluation algorithm that we presented earlier. Right, so in the earlier slide where we're talking about the policy evaluation problem or the strategy evaluation problem, we use bootstrapping to compute an evaluation. But that was an evaluation given a particular strategy. Right? But here we disregard we're not actually disregarding it, we just hide the underlying strategy, and the underlying strategy is no longer fixed. And then we're using a different Bellman equation, namely a Bellman equation where on the right-hand side we have this maximum operator. And essentially this performs two things. One is it perform a one-step evaluation of the current strategy, and because we're taking the maximum among all the actions, it's improving the strategy at the same time. Right, so you can see that although we are not explicitly repeating the evaluation and the improvement phases of the algorithm, this single Bellman equation does both of the job, right? So it does the evaluation, but not the complete evaluation, just one-step evaluation, and then it improves it straight away to calculate the maximum, to calculate the action which gives us a maximum value, right? So eventually it will converge, and we can guarantee that it will converge to the function V star. And then using the function V star and the previous equation that relates V star with the optimal policy, namely from the principle of optimality, we'll be able to get the optimal action for that state. Okay, so this is what we call the value iteration algorithm. If we want to compare these two algorithms, the policy iteration and value iteration, we'll see that value iteration in general requires less effort at each iteration. But in practice, you may find that if you apply policy iteration, the convergence can be done relatively quickly, so that we do not need as many iteration of improvement as opposed to the value iteration, where we need to repeat a lot of iterations, right? So there are pros and cons to each method. So just to summarize what we've covered in this lecture, we've introduced dynamic programming algorithm for essentially two problems that concerns with Markov decision process. First of all, we look at policy evaluation problem. This is a problem of computing an expected payoff of the player. Right? This is necessary because without this, the player will not be able to make actions. And then not only we want to compute the valuation, we would like to identify the strategy for the player which leads to the optimal payoff. Right? So that's the optimal control problem. We've introduced two algorithms, policy iteration and value iteration. And all three methods, also there's a method for policy evaluation, and then there are the policy iteration and the value iteration. So all three algorithms are based on essentially the same sort of philosophical idea or the framework, the algorithmic framework, namely dynamic programming. This basically for each dynamic programming algorithm we need a Bellman equation. Right? For the policy evaluation problem, we use the Bellman expectation equation. For the optimal control problem, we still have the Bellman expectation equation for the evaluation part, and then we combine that with greedy policy improvement and then iteration of these two. And then finally, for the value iteration algorithm, we combine these two using a single Bellman equation, namely Bellman optimal value equation. And that in one sort of round of the repeated iteration will get to the optimal value as well as the optimal policy. Right, so that's a summary for what we've done. We've introduced, so in this course we've looked at the single player case, not the multiple player case. And we've modeled the situation using a Markov decision process. So that's a very crucial concept that we introduce, which is a powerful notion that captures the interaction. It could be a dynamic interaction between an agent and its environment. And we've introduced these two problems, so policy evaluation and optimal control, and then we apply dynamic programming to solve both of the problems. Right, so that finishes today's lecture, and I will see you in the next lecture.